Hi everyone, let's talk about heating curves and phase diagrams. So first off, with the heating curve, as we're about to see, we are going to see the amount of heat or temperature or energy that you need to add in order to change from a solid to a liquid to a gas. And one thing that's really cool is you're going to see a bunch of horizontal lines on this phase diagram. On a horizontal line, the energy that you're adding, and it's kinetic energy, that kinetic energy is being used to change phase. So let's see what I mean. Here is an example heating curve. And it's worth, if you want, just kind of pausing the video for a second to really take in what is happening here, because there's some cool stuff going on. So, on your y-axis, you have the temperature of, let's call this water, right? And so initially you're at negative 25 degrees Celsius. So clearly this is ice. And as you go from negative 25 to 0 degrees Celsius, it doesn't take very much energy. So on the x-axis here is the energy. So from A to B, there's the energy that is required to go from negative 25 to 0 degrees Celsius, right? And this blue line up here from C to D, that is the amount of energy that's required to go from water that's liquid at 0 degrees Celsius and turn it into water that is liquid at 100 degrees Celsius, right? So again, not very far on the x-axis. And then finally, over here between E and F, we are going to go from water that is at about 100 degrees Celsius but is steam and turn it into water that is at 125 degrees Celsius, also steam. And you'll notice those gaps that I've drawn in green, they're not very wide, right? There's not a huge distance on the x-axis. So what is the space in between? What is the red space that we're missing? Well, that red space is the amount of energy, the kinetic energy that we're adding to do the phase change itself. So this first one, not huge, but bigger than from A to B, is the amount of energy that it takes to take water and turn it from a solid into a liquid. So all of the energy there, you'll notice we're adding energy, we're pumping in energy, we're going along the x-axis, but the temperature isn't changing. So all of that energy is going into the phase change. And it's way more drastic between a liquid and a solid. So all of the energy here is going into the phase change between a liquid and a gas, right? So you're adding energy, but the whole time you're staying constant at 100 degrees Celsius. So why is that? Because all of the energy that you're adding is going into that phase change. So this type of heating curve is pretty cool to see how much energy it takes to do the phase change itself relative to the amount of energy it takes to actually do the heating up. So comparatively, if you look at like this phase change here from liquid to gas, versus heating from 0 degrees, pretty much freezing, to 100 degrees liquid water, it's way more to do the actual phase change in terms of the energy that you need for doing something like boiling water. So kind of cool. Another thing that we need to talk about is called a phase diagram. So a phase diagram allows us to see a bunch of cool points. So let's open up a phase diagram here. And you'll notice that the greenish area in the upper left, this is your solids. And then in your blue area, you have liquids. And down in the yellow area, you have gases. And it allows you to see at a given pressure, so let's pick some constant pressure, what happens if you add temperature. So maybe 1 atm is like here, right? So at 1 atm for water, we add temperature, we're a solid, we're ice, we turn to liquid water, eventually we get to a gas, right? That's all well and good. That's kind of what we expect. But there are areas where if we had a really low pressure, let's say we were like down here, and we add heat to that solid, it turns directly into a gas. It bypasses the liquid completely, which is really cool. And also, if you start to think about this, there are two really funny points on this graph. So there's a point right here called the triple point, where whatever substance this is acting kind of as a solid, a liquid, and a gas at the same time. And there's an area up here called the critical point, where basically anything that's up and to the right of that point is a really interesting kind of liquid-gas combination, and we need to do those more justice. So we are going to see a video of both of those, both a triple point and a critical point, when we're together in class.